and relevant to your projects. But again, importantly, I posted the instructions for assignment 5 and 6. Oops. Assignments 5 and 6, we'll go through them quickly today, but take a look at it. I also posted an article on the financial model. So let's jump right into those instructions first. Actually, before I do that, maybe just take a quick review of the schedule, where we are. So we are here November 3rd, election day. We're going to talk about luminescent concentrators. It's a little bit of a short lecture, so I'll spend a little time on the instructions for the last 2 assignments. Assignment 4, of course, is due on Thursday. So for those of you who are presenting in class, make sure you're prepared. The section 90 students, make sure you present submit the videos. Next week, we'll talk about light extraction and light trapping in a bit more detail. And then the following week, actually, I had to change the schedule. November 17th was going to be a guest lecture from Apple, but I had to reschedule that. So that's we're going to talk about a few other topics, remaining topics in photovoltaics. And then the guest lecture from Apple is moved to the week of Thanksgiving. So just be aware of that. We also have 3 exciting guest lectures coming up end of the semester, one from Intel, Apple, and finally from Googlex. And the last assignment is due 6. Also a reminder that assignment 5 is essentially submission of the business canvas. I also changed that a little bit, so we'll talk about that. Okay, let's jump right into this. Whoops, wrong paper. Okay. So assignment 5 is due November 17th, just a couple of weeks. And all you have to do is submit your initial and your final business canvas. Now, what does that mean? That means first version of the canvas, many of you already submitted it. So I would say when you actually submit it on the 17th, if you can include that, that would be good, because I want you and for me to also easily see what changes were made. Most importantly, you need to interview potential customers, or this can also be partners or hypothetical customers or people who can give you some feedback, right? It can be anybody. I just call them potential customers, at least 3 more. And again, interview means you can just call them on the phone, send an email. It's not like you have to meet in person. And again, cold emails, cold calls are fine. If you want an introduction to someone, let me know, but you can also just ask your family, right? Some of these projects you're working on are directly relevant to that. Now, what does it mean? What is this interview for? This interview is for checking or correcting the hypothesis that you put in your first version of Canvas. So as we talked during 2 weeks ago, when we did the Canvas, we made some guesses on putting in. I want you to verify those guesses, and if they're wrong, correct them. That's the purpose of this interview. Okay, you have 2 weeks to do it. And then finally submit the revised version of Canvas. So this is what's due on November 17th. Okay, so again, due November 17th. You can submit on Canvas or email. Canvas, email, Slack, whatever you want, just as PDFs. Just a presentation. Any questions on that? Is everyone's pretty clear? Okay. Then the last one is assignment 6. Okay, this is the final assignment due on the last day of class, December 3rd, where you will present the commercialization plan in class. Again, section 90 students will present this as a video, submit a video. So there are 2 parts to this. For the section 90 students, there's only 1 part. We can combine this into a single presentation. But the students who are doing the in-class version or the IVC version will have 2 parts. One is the presentation in the class, and second one is submit a short form video pitch. It has to be very short, 90 seconds to 3 minutes. Shorter, the better. And we'll talk about what needs to go in there. Essentially, the goal of the business presentation or a product, it can be a product demo, it can be a presentation, anything else that you can convince, that you can use to convince an investor or a strategic partner to participate with you, to support you. The sections that are required, and this is important because this is new, and I will present it now, and if you have questions, please ask me. First, you'll have a brief elevator pitch for your company. Okay, this is for the presentation, just so you know, in class, or for those students who are making a video. Number two, there's something called a go-to-market strategy. Answer these questions. Who will be your customers? Describe your engagement/discussion with them to date. Have you validated their needs? Prove that they will buy from you with some either, there are many ways to do this, or how will you acquire the customers? Number three, market and industry analysis. How large is your market? What market segments are you going after and why? For example, if you talk about the outdoor recreation market, that's a pretty big market, but you might be going after folks who are going on short 2-hour hikes, not multi-day trips. And so that's a market segment, for example. This is an example. It may not apply to you. And why? So make some guesses, educated guesses. Is the market growing? How fast? All of these stuff, by the way, you can do research either through the university library. The librarians can help you. Again, remotely, you can email them, ask them for help, or just do the research yourself. How will you displace incumbents? What is your channel partnership strategy, if any? And obviously, a lot of the output, this stuff will come from your business canvas. So that's why this assignment is after you do your final business canvas. Section 4 is the technical product description. Briefly describe what it is. Technology validation. What evidence can you present that your product works as advertised? If you haven't built anything, which is perfectly fine for this class, plans. What are your future validation plans? Remaining product development risks, what's remaining, and your plans to overcome them, which can be technical, but it can also be market risk as well. For example, you're worried that it's too expensive for a customer segment. So if that's a risk, then you need to have a way to mitigate that risk. How can you reduce the price? Products advantages for customers versus other options. So that comes directly from the value proposition portion of the canvas. If you have IP, how will you protect it? And you heard a little bit about this in the last 2 lectures. Can others copy your ideas? Number 5, economics, very simple financial plan. I will show you a post to a Medium article that I posted today, which will help you formulate that, and some thinking through about how would you raise funding, what milestones would you think you would need to raise more funding in the future. This is really, of course, a thought exercise as a team. Finally, describe your team and why you are the best people for this innovation, this commercialization. And that's it. So that's, I know this assignment 6 is very new for a lot of us as engineers, but this is very important you spend some time. So you have about a month to work on it, and it really also is informed by the canvas. So this month, I want you to work as a team, really focusing on this as soon as you're done with assignment 4. Let me know if there are any questions. No. The last point is this link that I posted to a Medium article about financial modeling for startups. This is from a company called SlideBean, which is a startup. It's been a few years, and it's a really useful article. It's worth reading. It's fairly short, and there's a video accompanying the article that you can watch to really get a sense for what they did. So it gives you an idea of some very, very simple financial modeling that you can use that will help you really think through some of the numbers. And as engineers, of course, we all love numbers, so it's important that you do this. And I think this will probably be a little bit easier for you than some of the other parts. Okay. Are there any questions about the assignments? Okay, let me see, is anyone waiting to be let in? Nope. I see some chat. Let's see what. Exam grades, okay, yeah, this week. Any other questions about the assignments? Everyone's okay? Okay, don't wait till the last minute, because I know everyone will get busy with finals. So my advice is get started soon. Great. So again, just to confirm, you have 2 things you need to submit. Well, only 1 thing to submit, but you need to prepare for 2 things. 1 is a present in class, and 2 is a very short video pitch. Okay. I should also make a quick point that for those of you who are very interested in this, please look at the Venture Well website, which is based on the last class lecture. And you can actually submit an application if you're really interested in pushing this. And this is a really good experience because then you can actually go through a vetting process through Venture Well. For those of you who attended last week's lecture, you know what I'm talking about. So you can actually take your assignment 6 and turn this into the pre-application for Venture Well. So that's actually, it's outside the class, so it's not mandatory, but I highly recommend it. Okay, so then let's dive into today's subject, which is luminescent solar concentrators. And I want to spend first half of the lecture talking a little bit about the theory and the limitations of this idea. And then roughly the second half of the lecture talking about a few interesting applications related to energy and outside energy as well. So first, the goal, what is a luminescent solar concentrator? A luminescent solar concentrator is typically a piece of glass or plastic. So you can see it here, which is doped. So it's transparent, first of all, like a window, but it is doped with some material that absorbs sunlight and re-emits or fluoresces at a different wavelength that is now trapped within the glass and gets concentrated at the edges. So you can see the edge here is much brighter than the top here. And that's because light is being concentrated at these edges. Now, if you place a solar cell at this edge, now you can convert that light into electricity. That's the idea. So you can see what's happening is that light is collected from the entire aperture, this entire surface of this window, but it's concentrated to a small area right here. So that's why it's called a concentrator. Okay. So why do this? First of all, the most important reason, in my opinion, is the fact that this is actually a non-tracking concentrator. You don't need to track the sun. So that has lots of really nice properties, as many of you know, because you're already thinking about these for your projects, right? The other reasons are potentially you can reduce the cost because the plastic or the glass that's used here to host this material can be very low cost. You can imagine building integration, for example, it can be a part of a window, and this is kind of one of the main reasons people are pursuing this. You can have a little portion, for example, integrated into the window of a home, and it doesn't track the sun, but some of this light is actually absorbed by these molecules, and they can be re-emitted into the glass and then collected in a solar cell to generate very low amounts of electricity. Again, just to reiterate, concentration is achieved by collecting the sunlight over a large area, which is the window, and directing it to a small area of the solar cell absorbing materials, which is at the edges. Okay, now let's try to understand this a little bit better. The luminescent solar concentrator, we will refer to this as LSC, consists of a transparent material, which is this orange stuff here, that has been doped with a fluorophore or multiple fluorophores capable of absorbing incident solar radiation and emitting fluorescent photons. So sunlight's coming in, as you can see, and it's absorbed by these molecules that are embedded within this. And these molecules that are embedded within these will essentially re-emit. So it will absorb these photons and fluoresce at a different wavelength, and we'll talk about that briefly. And that light is now trapped within this host material, typically a glass or a plastic. And then it is redirected to the solar cell as shown by the arrows. So light comes in, gets absorbed, then it travels across the glass and then reaches the solar cell, which is shown here at the edge. Okay, so first question I want you to think about is, what is a concentration factor? So let's imagine we have a window whose length is L and width is W. And let's say it's thickness. So this is the top view, and I'm going to draw the side view. So this is the width, and this is the thickness. Let's call it T. And let's imagine the solar cell is placed across all the edges. Okay, so there are 4 solar cells, one here, one here, one here, and one here. What is the geometric concentration factor, and how would you calculate it? Does anyone want to guess? Well, hopefully you know this by now. Remember, the concentration factor is how much light, what is the area over which light is collected, which is this top area, which is length times W, which is where you're extracting the light. Sometimes you might have 2 sides, right? If you have a transparent window, you could have light from both sides, divided by what is the area of the solar cell, which is W times the thickness T, but there are 4 of them. There are 4 sides here, times 4. So the concentration factors, I can cancel that, cancel this, is simply L divided by 2T. So L is the length of the window, and T is the thickness of the window. Of course, the thickness of the window is much smaller than the length, so now you're talking about pretty large amounts of concentration, which is fantastic. Okay? So L is much larger than T, so you're talking about pretty big amounts of concentration. So that's the reason to do this, and there is no need to track the sun. That's why this is a very exciting concept. Now, let's also think about the fact that there's light trapping that needs to happen. Now, what does that mean? We've seen this before. Again, just to understand the physics of what's happening, light comes in, of course, from the sun, and it refracts into the material following Snell's law. This is Snell's law, right? Then it's absorbed by this molecule here, and that molecule then re-emits or fluoresces, and that's shown by this arrow here. And a portion of that light is trapped because of total internal reflection, TIR. And that happens when the incident angle theta is larger than the critical angle theta C, which is sine inverse, just remind ourselves, of 1 over n. Okay? Now, then we already done this in our lecture on light trapping. What is the probability that the light will be trapped? It is basically given by the cone angle subtended by this cone divided by the entire hemisphere, because light's emitting in all directions. Again, we will talk about this in some more detail. And that's the trapped light, and once it's trapped, it will bounce around and until it reaches the solar cell at the edge here. Okay. Now, the question is, if this works so good, why don't we see this? I mean, I told you that the concentration can be very high, it doesn't need to track. So why is this not more successful? There are 2 main reasons, I would say. The first one is described in this slide. So the first challenge is the low efficiencies. You end up with materials that generally have very low efficiency. This means that this process of light photons coming in from the sun being absorbed by this molecule and then re-emitted, that is a very low efficiency process, typically. Okay, that's one problem, and we'll talk why in a second. The second problem is the poor photostability of these materials. That means these are typically organic molecules that if you put it under sunlight for a long time, which has pretty significant UV, and if it gets heated up, it will degrade. So that's shown in this plot. This is an experimental measurement of a organic solar cell which shows the short circuit current as a function of temperature time at different temperatures, increasing temperature here. So you can see as time goes by, of course, these organic molecules will degrade. They essentially bleach over time. So the short circuit current decreases. Now, the decrease is much faster at higher temperatures. So this is at 50 degrees, and this yellow is at 70 degrees. So it's much faster degradation. And this is the main problem. And this is can be solved in many ways. One of the ways people are trying to solve is to find better materials. Things like quantum dots that you might have heard of, rare earth materials, semiconducting polymers, and things like that. By the way, quantum, these are what are called organic solar cells. Now, these are almost identical to things that you're carrying in your pockets today. And what I mean by that, these are very similar to organic LEDs, which, by the way, is on your phone's screens. So this problem can actually be solved. Of course, your phone OLEDs or organic LEDs or OLEDs that you've heard of, the problem of photostability on OLEDs have been solved primarily by packaging, by making sure there's no oxygen when you package them into displays, which is why your phone can have now beautiful OLED displays. Okay, so this is a problem that can be solved. In the case of solar cells, of course, the incentive is a little bit different because the price one pays for a nice OLED screen is much higher than one would pay for an organic solar cell. So again, that's an example of a business decision that's actually determining the technical application. One question I have, and this is I'm going to leave this as homework for you, is can you come up with an optical solution? And this, I'll give you some hints. One hint is the fact that we talked about the fact that UV radiation and heat are some of the key problems that affect the organic LED. UV is a different wavelength of light than the light that is visible. So could you somehow put a filter in front of the organic material to get rid of the UV light? So that could be one way to do an optical solution. Same thing with heat. Heat, of course, we know is infrared light. So if you can somehow filter out the infrared, then there's a way to minimize the heat. So those are example solutions, but you can come up with others as well. Now, let's try to quantify the performance of a luminescent solar concentrator by calculating the efficiency. And this is this is done by something called a Gertzberger efficiency equation, named after the professor from Austria who actually studied these many decades ago. What is the efficiency when we talk about solar cells? It is the fraction of incident power. Well, right now we're not talking about the solar cells themselves. We're just talking about the efficiency of the solar concentrator. And this is essentially the fraction of the incident power that reaches the top surface of the the glass, divided by the, sorry, maybe I should draw it. It's a fraction of the incident power. So this is our luminescent concentrator. Our solar cell is at the edge here. This is the incident power, right? P incident. And this is the output power to the solar cells. So the efficiency is essentially given by the total power that reaches the solar cell divided by the total incident power. Okay. Of course, to get the full system efficiency, you have to multiply this by the efficiency of the solar cell itself, right? We're not talking about that yet. And that depends on the solar cell, of course, that you use. Okay, so in order to estimate this, we have to understand the physics of the loss mechanisms that will happen. So here it is written essentially as a product of the efficiency of all the possible loss mechanisms. And those are all these different terms here, and we'll talk about each of these. Okay, the first term here is 101 minus R, which is a fraction of incident light transmitted into the sheet. Of course, we know that some of this light is essentially reflected out, right, just from the surface here. And that we'll call power reflected as R. So what's transmitted in is simply 1 minus R. And for broadband reflection, we know that this number goes as n-1 whole squared divided by n+1 whole squared, which is approximately 4%. So 1 minus r means it's about 96% for glass, n equals 1.5, or most plastics. It's pretty close. The second term here is PTIR. It's also something we're familiar with. It's the probability of total internal reflection, which is how much light is actually trapped within the glass or the plastic. And that, of course, is we also have seen before in the lecture on light trapping, is determined by the critical angle here, given by that. And it's approximately given by square root of n squared minus 1 by n. And it turns out to be about 75% in the case of n equals 1.5. So there's quite a bit of light that's lost here, which is, of course, expected, right? Because we know from this picture here, oops, sorry. This picture here, if the light that's coming in at an angle that's less than the critical angle, of course, it just escapes out on the other side. So it doesn't reach the solar cell. This is gone, right? And we know most of the rays actually do that, right? It's only a small cone angle that's actually trapped, given by this thing right here. So that's why you have that, that factor there. Okay, coming back here. The next term is something called absorption efficiency. Let's see what that means. It is, what is the probability that the photon is absorbed by the molecule? So again, the picture we have, you should keep in mind, is this. Light's coming in, and this photon, this purple line here, is absorbed by this molecule. What is the probability that that happens? It's not always the case that it can be 100% absorbed. So that efficiency, of course, must be as high as possible. And for that, the LSC, the material, the molecules must be designed to absorb the greatest possible range of wavelengths with the corresponding photon energy greater than the band gap the cells use. So of course, the solar cell itself cannot absorb light whose energy is less than the band gap. So the re-emitted light has to be at wavelengths that correspond to energies greater than the band gap. A good example is silicon. So if we think of silicon as the solar cell that we're planning to use to absorb the light and turn it into electricity, then the LSC must absorb all the wavelengths less than 950 nanometers, which is less than means higher energy, and emit in the 950 to 1000 nanometer range, because that's the range over which silicon can very efficiently convert photons into electrons that we saw in the review lecture on solar cells. This is where silicon has the highest spectral absorption. So that gives us a design parameter for designing those molecules that will absorb sunlight and re-emit in this region. And a typical number for this number is about 71%. The next term here is something called the photoluminescence quantum yield, which is essentially once the molecule absorbs the sunlight photons, it has to re-emit. What is the probability with which that re-emission happens? Because the molecule, once it absorbs photons, can do many things. It can do other things other than re-emission. There are other quantum mechanical processes that happen. But what is the probability that re-emission actually happens? Again, that's not 100%. For those of you who might have played around with a fluorescence microscope, you know what I mean. You have to use a very bright source to excite the fluorescence, and the amount of fluorescence that you see is typically very weak. For those of you who might have done some fluorescence microscopy in their high school or undergraduate years. Maybe an even more common example would be those materials that do photoluminescence. So those children's toys, for instance, which you put it under a lamp and then you turn off the lamp, it will glow. Of course, the lamp has to be very bright in order to excite that photoluminescence, and the amount of light that you see once you turn off the lamp is very, very, very weak. So that means that the efficiency of photoluminescence is very low. And that's generally the case. We'll talk about why in a second. So that's this term PLQY. This is the probability that an excited fluorophore is a molecule that has absorbed the incident photon. It will decay, it will lose that excited energy by emission of a fluorescent photon. This is a very complex process, but we'll talk about this in a very simple sense next. So the photoluminescent quantum yield can be written very simply as the number of emitted photons, that's this numerator here, divided by the number of excited molecules times 100%. We want this to be very high. Typically, we want this to be like 95%. If it's properly tuned, you can get this to be quite high as well. And there's and these two things are related. So the next term is something called the Stokes efficiency, eta Stokes, and that number is about 75%. Now let's see what that means. To understand Stokes efficiency and the photoluminescent quantum yield, we need to understand fluorescence. So fluorescence can be understood from the discrete energy levels of a molecular system. And this, of course, comes from quantum mechanics. And you have learned this in your high school physics or high school chemistry. So it's mostly a review. Let's see what happens. So you can draw the energy level diagram for a molecule starting with the ground state, which is where everything is resting. That's the natural state of being. If you come in with an excitation photon shown by this green wavy light here, photon comes in, gets absorbed by the molecule. It gets kicked into an excited state because now it has more energy than in the ground state. It reaches some excited state shown here, but it very, very, very quickly relaxes. It loses that excess energy and reaches the band edge as shown here. So this is a band gap. For those of you who have done semiconductor physics know what I'm talking about. And this is the edge of the band, or the band edge. Now this process is called a relaxation process, happens extremely fast. This is a quantum mechanical process where essentially energy is lost in the form of phonons, which is essentially a manifestation of heat into the rest of the host matrix or the crystal structure, if the molecule forms a crystalline structure. So this is not so important for us, except the fact that you have lost some energy. This is related to the Stokes efficiency. Then, if we are lucky, or the molecule has been designed properly, it will relax back to the ground state by emitting a photon. And this is the fluorescence that we actually see. Okay, so you can see this is a very complex process. Again, light comes in, gets absorbed, the molecule goes into a higher energy state, it relaxes, then it relaxes back down again to the ground state, emitting a photon. So one photon came in, one photon came out. The question is, if I have 1 million photons came in, how many photons came out? Is it 0.9 times 1 million? If so, my efficiency would be 90%. Okay, now this efficiency is eta photoluminescence quantum yield multiplied by eta Stokes. Now, what is Stokes? You can see the energy of the photon that was absorbed is this much, but the energy of the photon that was emitted is this much. So the energy out is actually less than the energy in. And that is the Stokes loss. And this is the Stokes shift. And this manifests itself in the spectrum. If you ever think about fluorescence, the excitation happens at a shorter wavelength, which is my E in, and this is my E out. Emission happens at a longer wavelength, and E in is actually always greater than E out. Unless you have very special situation, can be actually less, but we won't talk about that. Which is, by the way, why when you do fluorescence, you typically try to use UV light, right? So for example, if someone's doing forensics and you're looking for blood, you use a UV light to see, right? And the reason is UV photons have lots of energy and they will excite essentially fluorescence from hemoglobin in the blood, which will absorb the UV and emit in the blue. So the UV wavelength is of course shorter than the blue wavelength, and the UV photon has more energy in than the blue photon. So a similar sort of thing happens here in LSC as well. So again, that will be 95% in terms of the photoluminescence quantum yield, and Stokes efficiency typically about 75%. Okay, Now we have a pretty decent understanding of all these parameters. The remaining things are relatively simple. Something called eta host, which is a host efficiency. This is the loss from absorption of the trapped fluorescence. We know that the photon that's emitted from the molecule is bouncing around here, right? So when it's bouncing around, this material itself, if it's not 100% transparent, might absorb some of this light. Typically, if you use a good host material, like a good plastic like PMMA, which is plexiglass or glass itself, this can be very low. Typically, the efficiency is like 95 to 98%. I mean, the loss can be very low. Then the second last term is something called the efficiency of TIR. We said that theoretically, total internal reflection is 100% efficient. However, if the surface is not perfect, if you have scratches and stuff, some of this light can actually escape out, which you can actually see if you take a piece of plastic and shine light on it. You will see that the edges of the plastic are bright because some of the light's trapped. Now, if you scratch that plastic, you will see that scratch is very bright because some of the light's actually coupling out. Very simple experiment to try. However, if you have a very nicely nice surface, this efficiency can be very high. And the last term is something called self-absorption. This turns out to be the most important and most limiting factor. This is basically the fact that here you saw, and I'm draw this with a different color. You saw that this molecule emitted this photon that's bouncing around, but I have other molecules sitting around in my material. And if this photon, for some reason, let's say I'm going to draw a different photon here, reaches this molecule, that could be absorbed again by this molecule. And that's a problem because now that photon is lost, right? It's not going to reach the solar cell, and that isn't lost. And that loss is actually the reason why you cannot arbitrarily increase the concentration factor. The larger you make the window, the longer the emitted light has to travel to reach the solar cell. And the longer it travels, the higher the probability that it will be absorbed by other molecules in the host matrix. This is why you cannot beat the second law of thermodynamics using this approach, which if you are a very astute observer of these lectures, you might have asked that question. In any case, that's a very interesting point by itself. Now, so that's the whole idea, is that the fraction of fluorescent photons reaching the edges of the LSA sheet without being lost due to reabsorption. This depends on the concentration, of course, how many dye molecules are there, and the quantum yield, like how efficiently will it absorb. So typically it ranges from 40 to 80%. So that's a bit of a problem. Now, if you multiply everything together, the
Professor Menon, we can't hear you.
I think I have a problem with my connection. Hold on a second, okay? Okay, I should be back now. Can someone say if you can hear me? Sorry about that.
Now.
Yes.
Oh, okay, perfect. Sorry about that. I think the kids are on their class, so that's probably one of the reasons. So let's see. Let's go back. I want to play, what I was saying was that I wanted to play a quick video about these transparent solar cells. So let me pull that up. And I'm going to play it. I want to make sure you can hear that.
I'm here on the waterfront in Detroit, and I'm talking about solar power. When you think
Is
of
that,
traditional solar panels, you think of those large black squares. Detroit, and I'm talking about
Can you
solar
hear
power.
this, or
when you
is
think
that
of
too
traditional
soft?
solar panels, you think of those large black squares that are mounted on rooftops or in fields.
Okay.
But what if we
So
were able to
it's
start
pretty
getting our
short, so
solar
play it
panels to
quickly.
look like this? An entire skyscraper dedicated to harvesting solar energy. A Michigan State professor is making that happen right now.
And
So I'm sitting here with Professor Lunt, a professor in the College of Engineering.
Correct. I'm a professor of chemical engineering and material science. When I was growing up, I grew up just outside of Boston, and I began to appreciate the amount of area there is in not only glass, but just tall buildings in general. And there's often more area in the vertical footprint than there is in the rooftop footprint. One of our thoughts was if we could turn these areas into solar harvesting surfaces, we could really make a big impact. This is a transparent luminescent solar concentrator. The way that this works is it's going to capture the parts of the solar spectrum that you can't see with your eye. So it's going to capture the ultraviolet and near infrared parts of the solar spectrum, and that glowing infrared light gets guided to the edge of the glass, where we mount very thin strips of solar cells, and that's going to convert that energy into electricity. So now we are in the molecular and organic exotonics laboratory. And so this is a fully assembled prototype of this type of technology. So I guess what we can do at this point is just hook this up and show you kind of how it works. So what I'm going to do now is just hook up the solar concentrator, and we're going to shine the light onto the active layer, and the fan moves.
Generating power.
That's right.
So with much bigger windows, with the actual power of an intensity of a sun,
That's right.
you're going to do more than just be able to move a little fan.
That's right. We're going to be able to power the building. Any building can start to be a good solar collector now. So we can turn our solar farms into solar cities.
When you're looking at a building like this, if we implemented your technology on this, how would this building look different?
So the building would look exactly the same.
It'd just be normal windows.
That's right.
That's the
That's
benefit, right?
That's right. And whether you're talking about the windows or the siding, the building will look exactly how you want the building to look, and you won't even know that the solar technology is even there.
Is this something that could be retrofit onto old buildings?
Yeah, that's actually a very important part of this technology, is we actually have the ability to not only integrate it during the window manufacturing process, but we can also make laminates where we can retrofit from the inside of the building. And so this type of technology allows us to really think about new construction as well as existing construction, but also other applications such as mobile electronics, automobiles, greenhouses. So the applications are almost endless. We have glass up there, we have glass down here. Because we've developed this really scalable process, this really scalable technology, I think we can start to see this within a couple of years in products. So that's our goal, is to see products in a variety of areas within the next couple of years.
So this isn't some far-flung thing. This
is happening now. Yeah.
Okay, great. So you get an example of oops, what's that? Okay, so sorry about that. Can someone say if you can still hear me?
Yeah,
Yes or no?
Yes, yes.
Okay, great. If you do get disconnected, if I get disconnected, let me know, because I can't see the Zoom while I'm sharing the screen. Okay, great. So I want to talk about 3 more applications which are relevant. First is a very interesting paper from Facebook Connectivity Labs. So, and the paper is actually linked on the class website, so feel free to take a look. It's a fairly nice paper from a couple of years ago. Now, Facebook's interest here is something called optical communications. So in other words, they want to essentially network the entire world, right? If you're a village in Africa, it's very hard for you to get, internet connection through cable. So instead of cable, the idea is that you can communicate with light, but free space light. Instead of a fiber taking communication signals, you can simply use a laser beam to essentially send the signal from the village, some sort of cell phone tower on the village, to something flying high up in the sky. So there are lots of examples of this. Facebook's idea was to have drones flying around. I think Google had this idea for what they call Loom, which was essentially big balloons with routers and so on. So all of these essentially rely on laser beams talking to each other. So you need to essentially send a laser beam across very, very large distances, kilometer distances, and collect that laser beam and somehow measure its intensity and how its intensity is varying with time, which is basically, intensity modulation or amplitude modulation, similar to what radio works, right? For those of you who are doing communications, they're probably very familiar with this. So that's their goal. And what I'm going to show you is an example of a luminescent concentrator that they use to collect the light from a beacon, a laser-based beacon, which is very, very, very far away, kilometers away. Okay. Now the problem with why is it so difficult to collect? It's difficult to collect because when you send even a laser beam across vast distances, kilometers, the light tends to spread out. So the beam, even though you start with a very tiny beam at the beginning, if you look kilometers down, the beam gets huge, meter sized. And the problem with very big beams is that in order to collect that signal, you need big optics, you need huge lenses, and that's a big problem. And especially if you have a balloon swinging around in the air, you cannot point it very precisely, right? You cannot have a lens that is very precisely pointed to the laser, and the laser might also be moving around. So you need a way to somehow collect this light, which doesn't have to track that laser. So this is why the non-tracking property of the luminescent solar concentrator becomes very interesting. So that's exactly what they did, and this is a very simple schematic. So you have essentially a laser beam coming down here. This is the luminescent concentrator, essentially a little strip of plastic that you can see a photograph of it down here, which is embedded with some molecules that will absorb that laser light and re-emit in a different wavelength. So this is it doesn't have to be laser, it can be an LED as well. So in this experiment, they used an LED, and this is the fluorescence. So it's green. So they absorb in the blue and emit in the green, and that emitted light is essentially trapped inside this, and then and then it's drawn into like a fiber. And this is a familiar picture of light trapping. Blue light comes in, green light is emitted. Some of it's trapped, some of it has escaped. And then you have some conventional lenses and then a detector. APD refers to a avalanche photodiode. So it's a way to essentially measure the intensity of the light. It can be very fast, so you can do time division multiplexing to send communication signals. So that's exactly what they did. So this is their experiment. They had this big strip of luminescent solar concentrator, which is illuminated in this example by a 405 nanometer laser. It's driven. There's a laser driver, and there's this is the modulator that they use to send some signal. And here again, the LSC is collecting the light. The green photons are emitted, and they're collimated by these lenses here. It's a simple telescope. Then this goes into an APD, and then oscilloscope essentially measures the output of the APD. And this has some signal, that they actually capture. Of course, what's really cool is that you can actually do this in a omnidirectional fashion. So by essentially turning this little strip into a bunch of fibers that can essentially mesh all the way around, you can capture this light from the laser light from any direction. And this is really difficult to do other ways. So this is a very cool design that they came up with some 3D printed parts, and this is a photograph of the design. And you can see the green light here, and that's because the green is the fluorescent light, and some of the light's actually escaping, it's scattering out into free space. So what you're seeing with your eyes actually are captured by this camera is actually the lost photons. The photons that are not lost needs to go in here to the detector. So it's a really interesting example of how an LSC can be applied in optical communications. By the way, this also has lots of interesting applications in space-based communications. So as you might have heard recently about the SpaceX launching a network of satellites to create, again, internet connectivity across the world, across the planet. And the way the satellites, they have to communicate with each other, they communicate in space directly with laser beams. And there are lots of really exciting stuff happening because you can apply quantum cryptography to these optical communication links, so you can have almost unhackable communication channels and so on. These are all very, very hot areas of research today. A second application back to Earth is in agricultural lighting. This is a very, very interesting company that I found based out of New Mexico called UBQD. And of course, QD refers to quantum dots. And what they do is very cool. So the final product looks like this. So they have a greenhouse where they want to grow some products. And we know that the plants prefer certain wavelengths of light for the most efficient photosynthesis. So they designed these luminescent concentrators, which can be excited by an LED, but will emit at the wavelengths that the plant is interested in. And because you can actually put them in fibers and send them down close to the plant, you can have a very efficient delivery of light to the plant. That's what's implemented here. And this is an example of what it looks like. So here, this is the LSC. It looks orange because it's emitting in the orange, which is what the plant's like in this example. And the excitation happens with white light, or typically with blue LED, but in this example, they're just using white light. And there are many versions of this. So this is a fiber-based solution. So they can put an LED at one end of the fiber. There's a hollow core fiber with quantum dots embedded inside it. So there are quantum dots inside here, which is the same stuff as we had in the LSCs, and then which will absorb the blue light and emit in the wavelength that the plants want, and the fiber will guide it to the plant, as shown here. Acts like a flashlight. You can also have segments with different quantum dots emitting different colors. You can also have LEDs like that, which are placed outside, which is simply exciting from the outside. And that's exactly what they do in this picture, is they have LEDs in the ceilings or on the sides. I think, I'm not sure for sure, but I'm pretty sure that they have some LEDs simply exciting these luminescent concentrators from outside. And this is another example where they have a LED illuminating a small section of the fiber, which has the individual or mixed quantum dots, and then they have another section of the fiber to deliver the light to the plants. So again, another very interesting application of LSCs being commercialized by this company. And the last example I want to talk about before we end is on wearable solar cells. So this is a paper that I recently found actually a couple of days ago, and I posted on Slack. Some work from the Swiss Federal Lab for Material Science and Technology. And essentially they want, because these LSCs can be very thin, they came up with this idea of putting this material in something called PDMS, which is a very flexible polymeric material, which can essentially be made into textiles. So you can make these really nice flexible materials. So you can imagine you have a shirt that is essentially fully a solar cell. So it is generating energy. It can keep you warm, or if you have inbuilt heaters, or you can have lights, whatever, for fashion. So another interesting application. And that's my last slide, and I will stop here and see if there are any questions. Oops, let's see, something on chat. Okay. I turned off my video before because I was afraid my my Wi-Fi bandwidth was long, but okay. So yeah, if there are any questions, feel free to ask. If not, we'll end early today. Take advantage of the time to the extra time to work on the assignments. Remember, assignment 4 is due Thursday. Assignment 5, which is the business canvas version, is due November 17th in two weeks. And last assignment is due the last day of class. Okay. Okay, are there any questions? Okay, I don't hear anything, but again, feel free to ask on Slack. I'll respond pretty quickly if there are any. If they're not, then I suppose we can end. And if you haven't already, go and vote if possible. Perform your civic duty. Okay, good luck, and see you all on Thursday. Thank you. Can you still hear me? Right, okay, great.